The graph shows the variation with time of the speed of a ball that has been released from rest. The force of air resistance is not negligible. State without any calculations how the graph could be used to determine the distance fallen. The distance fallen is equal to the area under the curve. The next question. In the space below, draw and label arrows to represent the forces on the ball at 2 seconds. There are the next forces on the ball. The gravitational force or weight, or just mg, but not gravity, downwards, and the force of air resistance upwards because it opposes motion. But what about the lengths of given arrows, because they represent the magnitudes of forces? So let's consider a graph, and we know that since it's VT graph, we know that the rate of change of velocity is equal to acceleration, and the rate of change is the gradient of a tangent drawn at some moment of time. And since we need a moment of time at 2 seconds, we should draw a tangent at 2 seconds, and we can see that a gradient of this tangent is positive, so there is some positive acceleration at 2 seconds, hence a ball is accelerating downward, so weight must be longer than air resistance. And the next question. Use the graph opposite to show that the acceleration of the ball at 2 seconds is approximately 4. So, to find acceleration, we should draw a tangent at 2 seconds and find the gradient of this tangent, and it should be approximately 4. Calculate the magnitude of the force of air resistance at 2 seconds. So we can see that there are two forces, and applying the second Newton's law, the vector sum of two forces is equal to ma, and we should consider forces in projection on some axis, let it be y downwards, and it becomes mg minus let air resistance be r is equal to ma. Hence r is mg minus ma, which is equal to 0.5 times 9.81 minus 0.5 times 4, and it's approximately 3 newtons. State and explain whether the air resistance on the ball at 5 seconds is smaller than, equal to, or greater than the air resistance at 2 seconds. We can see that gradient at 5 seconds is smaller, hence acceleration at 5 seconds is less than at 2 seconds, and we can see that air resistance is mg, which is constant, minus ma, and since ma is smaller, r is larger, so air resistance is greater than, or we know that air resistance increases when speed increases, and at 5 seconds speed is greater than speed at 2 seconds, hence air resistance is greater, and speed at 5 seconds is greater directly from the graph, or since an object is accelerating, definitely speed at 5 seconds is greater. And the next question. After 10 seconds, the ball has fallen 190 meters, shows that the sum of the potential and kinetic energies of the ball has decreased by 780 joules. So if we consider a point at the Earth's surface, so we can say that loss of potential energy is equal to mgh and is equal to 0.5 times 9.81 times 190, which is equal to 932 joules, and gain in kinetic energy is equal to mv squared over 2, and the speed can be found from the graph. It's 25, and hence it is equal to 0.5 times 25 squared over 2, which is equal to 156, and the required decrease in total energy is equal to 932 minus 156, which is approximately 780 joules as required. The specific heat capacity of the ball is given. Estimate the increase in the temperature of the ball. So when energy is transferred to some object, we know that energy required to heat something up, energy is equal to specific heat capacity multiplied by mass and multiplied by change in temperature. So applying law of conservation of energy, this energy is transferred into internal energy of the ball, which is equal to Cm delta T, and is equal to 480 multiplied by 0.5 multiplied by delta T, and delta T is approximately 3 kelvins. State an assumption made in the previous question. It may be that all the lost energy went into heating the ball, or no energy transferred to surroundings, or the ball was heated uniformly. And that's all for this question.